Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, shall we begin? All right, so Ryan is visiting us from Georgia Tech. For his thesis, he worked on a lot of tree-related algorithms, which he's going to talk about. But he also spent a great deal of time creating mlpack, which is a significant open-source machine learning system.
Okay, thanks, John, for the introduction. You're right, my name is actually Ryan, not Visitor, but I will respond to both. Okay, so before I get started, I do want to say that this work has really only come together in the past handful of weeks. So you are the first live audience to see it, other than my cats, and they weren't very interested. So hopefully you guys are more interested. So let's talk about k-means. So k-means clustering, I would wager a bet that everyone in here knows it. It's probably the most widely used and most popular clustering algorithm out there for a handful of reasons. The first is that it's simple. The second is that it's probably one of the first clustering algorithms taught in most introductory machine learning courses. Those two things are related. The third is it's reasonably fast. And the fourth is that it only has one parameter, which is k, the number of clusters. So just as some quick review, how does this algorithm work? We get our k initial centroids, and we get our data set S. We assign every point in the data set to its closest centroid. Then we recalculate the centroids with the new assignments. So the two barely visible centroids here in red and blue, I've colored along with a bunch of points. So your red points are closer to the red cluster, and your blue points are closer to the blue cluster. And then when we recalculate the centroids, after the assignment step, the centroids move. And you do this over and over again until either it converges for whatever your measure of convergence is, or until you get tired of it and Control-C it, or until it goes to the maximum number of iterations, what have you. Okay, so now the simplest implementation of this algorithm, it takes O of kn time per iteration, because we iterate over every point and we iterate over every centroid. Great, and so for the rest of the talk, let's just take n is equal to the number of points in our data set. So the next question, because this is a machine learning talk, we're going to talk about how to scale k-means. Everybody talks about scaling data sets. That is where the term big data does come from, after all. So people talking about scaling k-means usually talk about scaling n, the size of the data set. But it's less often that people talk about scaling k, the number of centroids. But it is relevant. For instance, if I'm coming up with a code book for vector quantization or local coordinate coding or something like this, I may do k-means clustering with k in the thousands or tens of thousands or maybe even more. If I'm clustering large-scale astronomical data, I may have k in the thousands also. So when I say, okay, let's say, okay, k is large and n is large too, what are we going to do? We have a number of approaches. The first is we can sample. We can just pick some of the points out of our data set of size n. This doesn't really work too well. It's known to work worse and worse as k gets larger. We also have approximation approaches. I'm going to set these aside because I'm more interested in the exact solution today. Okay? I'll come back to approximation later. We also can select our initial centroids in a more smart manner. I'm also going to set this aside because this is something that we can do on top of our k-means algorithm. My interest here is accelerating the individual iterations of finding the assignments of every point and then recalculating the centroids. So we have a couple algorithms that do this. The first is a blacklist algorithm, which builds a tree on the data, a single tree, and then iterates over all of the centroids, rules them out for certain nodes. Then we also have two other algorithms, Elkin and Hammerly's algorithm, which iterate over the data set sequentially and maintain bounds in the distance between points and centroids in order to try and prevent the computation of distances between points and centroids. And so these tend to be pretty fast, but they're not really tailored to the large K case. I should leave the cap off for convenience. So how do these algorithms actually scale? Let's just get it out in a nice table here. The naive algorithm, I already told you, it scales as O of kn per iteration. The memory usage is O of n plus k. We need to store the data set. We need to store the centroids. The blacklist algorithm, assuming we're using KD trees, which is what was done in the original papers where this was described, we have an O of n log n setup cost before we start. We build a tree on the points. Every iteration, in the worst case, can take O of k n log n in case we can prune absolutely nothing. This is not actually how it tends to run. It tends to be pretty fast. And then for memory usage, we store the tree, n log n, and we store the centroids, k. Elkin's algorithm, there's no setup cost, but during each iteration, we calculate the between centroid distances. That takes k-squared time. And then in the worst case, we calculate every between point and centroid distance. That's O of kn time. And the memory usage is the same because we maintain all of these bounds. Hammerly's algorithm does basically the same thing, but it maintains fewer bounds in memory, so we get better memory usage. Okay, and so now there's one more line in this table, which is what I'm here to talk about today, this algorithm called dual tree, where our setup cost takes n log n time. Our worst case runtime bound is O of k log k plus n asterisk, because it depends on some other things which I'll get to later. And then the memory usage is O of n plus k. Okay, so this algorithm is empirically several times faster than other algorithms, and if several times isn't enough for you, then all you need to do is keep making n and k even larger because it scales better than the other algorithms. Okay, so I called this the dual tree algorithm, so this means that I now need to explain what dual tree algorithms are. So I'm going to discuss the basic idea behind dual tree algorithms, sort of what they look like, and then I'm going to formalize it. So your typical dual tree algorithm, we build two trees, the query tree, T sub q, and the reference tree, T sub r. And the query tree, let's consider for one instance the task of nearest neighbor search. The query tree will hold those points for which we want the nearest neighbor, and the nearest neighbor will come from the reference set. Okay, so we have query points, we have reference points, query tree, reference tree. Once we build these trees, we're going to traverse them simultaneously. And as we do this, when we visit a pair of query node and reference node, we're going to see if we can prune it. And if so, we prune that whole subtree. We don't go any deeper. Otherwise, we perform some base case computation between points held in those nodes. Okay? Why do people care? Because these algorithms tend to be really quite fast. And we do have many of them. So we can solve lots of problems. We can do nearest neighbor search. That's one example I just mentioned. We can do kernel density estimation and kernel conditional density estimation. We can do n-body force calculations. We can do endpoint correlation function estimates. I can calculate minimum spanning trees. I can do max kernel search. I can actually even do approximate matrix multiplication, but I point that out not because that's, I don't think that is actually interesting in practice. I think it's interesting as a thought experiment. So, but you can do it, is my point. So we have all of these, and if you go read the papers, all of the algorithmic sections in them, they look very different. So then the question, which I'm going to ask and then of course answer, is can we generalize? And of course the answer is yes. We can come up with a convenient and modular abstraction through which we can understand dual tree algorithms. But first I need to bring in some notation. So the first thing is a space tree. And note this is not a space partitioning tree because I allow the nodes to potentially overlap. So you throw that out, we get space trees. Interesting mental image. So your tree is an undirected acyclic rooted simple graph with a handful of properties. First, every node holds a number of points, potentially 0, and is connected to a parent and a number of child nodes, potentially 0. There's one node in every tree that doesn't have a parent. That, of course, is the root. And every point in the data set is contained in at least one node of the tree. Maybe more, but at least one. Then, the last bit, every node corresponds to some convex subset of the input space that the points lie in that contains all of the points as well as the convex subsets represented by each child. So another way to say this is every node has some bounding shape that contains all descendant points. Okay? So here's a abstract representation of a tree. This tree happens to be binary. It could be a KD tree. But I point this out because I want to make one distinction here, which will be important for the rest of the talk. Each point can hold nodes. Each point can also have descendant nodes. These two things are different. So N13 here might hold a point or two, but that may not be the same as what N4 and N5 and N6 and N7 hold. So when I say descendant points, I mean the points, say the descendant points of N13, the points held in all of this subtree. The points held in N13 are the points held only in this node. And for, yeah?
Do the space covered by N13, is this always a superset of all of its children?
Yeah, by definition. Yeah. I am going to make one restriction for today that makes things a lot simpler. It is, I can rederive all the work I'm going to do without this assumption, but it makes life a lot easier. If I hold points in some node, those points also have to be held in at least one child of that node. Okay? So if I have a point that appears, it will also appear in lower levels. The cover tree satisfies this property, and KD trees in general, which only hold points in the leaves, or any other type of tree that does that same type of thing, will also satisfy this property. Okay, so the next definition I need to introduce, and I have to apologize for this one. I promise this is the only slide that is a wall of text. We need to introduce and formalize our traversal. So our pruning dual tree traversal is some process where we have two trees. We have a query tree and we have a reference tree, as earlier. We're going to visit combinations of nodes, a query node and a reference node, and we're going to visit these combinations each no more than once. When we visit a combination, we're going to perform some computation to assign a score to it. I'm going to call this a score function. Whatever that function is, we'll delay that till later. If the score is above some bound or infinity, we prune the combination. We don't go into any descendant combinations. Otherwise, we're going to perform a computation between each point in the query node and each point in the reference node. Now note, this is where the distinction comes in. I didn't say perform a computation between each descendant point. This is perform a computation between each point. So again, if I have a tree which only holds leaves at the bottom level, I will never call base case until my combinations are both leaves. Okay? So if we don't prune any nodes during the whole thing, then we're going to perform our base case once between every point in the query tree and every point in the reference tree. Okay, so this is our abstraction for a dual tree traversal. I won't visit this again. I won't really talk about what these look like. We're just going to assume that we have this thing. Okay, what does this get us? We have a type of tree. There are tons of types of trees. We take one. We combine it with a type of traversal. There are fewer types of traversals, but you could have many types of traversals. We could do breadth first, depth first, some combination thereof. Then we combine it with our problem-specific base case, our point-to-point function, and our score, node-to-node function. What do we get? We get a dual tree algorithm. Okay? What else do we get? We get really easy to understand and beautiful algorithms. Okay? And so this is opinion, but I think it's right, and I'm hoping to convince you of this by the end of the talk. More importantly, say I come up with a new type of tree, and this tree performs better for some type of data. That propagates. I can just compare that with a traversal and all of the problem-specific functions that I already have, and now I can say, oh, my new type of tree, I can do all of those dual tree algorithms. I can solve all problems that I can with dual tree algorithms with it. It eases the development of new algorithms, and I'm going to demonstrate this because when I come up with my dual tree k-means algorithm, we're just going to come up with these two things, plus a little more, but that will be the dual tree part of it. And when I sit down and I write this in code, this is a nice software abstraction that we can use. Okay, so implementation is eased. The guy who writes the tree doesn't even need to know the guy who wrote the base case and score functions. It's probably helpful, and like people should know each other in the same project, but you don't have to. So this is very nice. Okay, so let's take a look at a quick example of range search, wherein for every query point, we want to find every reference point which lies within a range parameterized. The lower side of the range is L and the upper side of the range is U. Okay, so the base case is pretty simple. We compare a query point and a reference point. We could actually write this on one line if we wanted, but I haven't for whatever reason. If the distance between the points is within the range, add the reference point to the list of results for the query point. The score function is also pretty straightforward. If the range of possible distances between the nodes, so the minimum possible distance between descendants and the maximum possible distance between descendants. So in this case, here is the minimum distance, and the maximum distance would just be a little wider. And add the radii or the diameters of the nodes. If that range doesn't overlap the target range, then no possible descendant combinations can even lie within the range. We can prune. Okay? And so we'll return infinity, like we're supposed to. Otherwise, we'll return 0. And you say to yourself, well, wait, why are we not just returning true or false for when we should prune? Okay, the reason is recursion order. If I'm doing something like, say, nearest neighbor search, I want to go to the best combination first. So this is why we return a number which tells the traversal, which may or may not act on it, depending on the traversal, which way it should go. Okay, but in the case of range search, the recursion order actually doesn't matter, so we return 0.
I didn't quite understand that. So inside the cover tree implementation,
yeah.
Is this half sort, basically quick sort, but only recursing on one side?
Yeah.
Which is helpful, substantially
yes.
helpful in terms of speeding things up.
Exactly. And so for the
with this?
yeah, exactly. This is actually sort of what that does. So for nearest neighbor search, I return as my score the minimum distance between the nodes, which is exactly what half sort I believe sorts on, and then we recurse based on that priority. Okay, so we've captured that. Okay, so before I move on, I kind of want to make sure we're all clear on my dual tree algorithm abstraction. So any questions? I'm going to drink some water. Okay, cool. Then let's move on. Dual tree k-means. So I want to develop an algorithm where we can do an exact iteration of the algorithm I showed earlier. It's called Lloyd iteration is what I'll call it. We want to do that exactly, and we'll incorporate a handful of pruning strategies. First, we will build our query tree on all of the points in the data set, and our reference tree on the centroids. Okay, so for every query point, we're searching for the nearest centroid. This looks like nearest neighbor search. I'll come back to that in a minute. Okay, so that said, we'll use 4 strategies for pruning and reducing our work. When we recurse down a particular branch of the tree that's built on the points, we should terminate early if we can determine that only one centroid can possibly own all of its descendants. When we encounter a particular node combination, we should prune if we can show that no possible descendant centroid can own any descendant query point. We shouldn't visit nodes or points when we can say that between iterations of this algorithm, the owner can't possibly have changed. And when possible, we should use some bounding iteration from previous information. So if I know that the distance between a point and a centroid is this far in one iteration, then I should try and reuse this information however I can instead of throwing it away next iteration.
What does own mean?
What I mean by, by own, so when a centroid owns a point, it means that the centroid is the closest cluster to that point. Okay, so when a centroid owns a node, then there's no closer centroid to any descendant point of the node.
Its own can't make sense.
Yeah.
So I guess I'm wondering, even if so even if the centroid might have changed,
Yeah.
Typically you might expect it not to have changed in a completely radical manner. So maybe
Yes.
maybe it moves to a point that's sort of close by.
Right, and that's
Where would that come in?
the using bounding iteration from previous or bounding information. Yeah. So we'll loosen the bound as much as we need in order to keep the work low. Okay, so a first attempt, I mentioned I come back to nearest neighbor search. This is a pretty simple idea. Here's how our k-means algorithm will work. First, we'll build a tree on the points. We'll call that T. And then each iteration will look like this. First, we'll build a tree on the centroids. And then we'll use our black box of dual tree nearest neighbor search with the tree on the points as a query tree and the tree on the centroids as a reference tree. And what this gets us a bunch of cluster assignments for each point, and we can then iterate over all of those and build our new centroids. Okay, and so this is cool. It gives us actually some nice theory, but the talk would be too short if I stopped here. So let's complexify this a little bit. Our outline or our algorithm at a high level is going to look like this. At first, we'll build a tree on the points. This is where our O of n log n setup cost will come from. And then during each iteration, we'll build a tree on the centroids. And then if it's not the first iteration, if we already have some bounding information, we're going to go through the tree and we're going to mark those nodes which we don't need to visit and those points which we know the owner can't change. Okay? And we'll also update our bounding information. We'll loosen it as necessary. Okay? Then what we'll have is we'll have a tree with lots of nodes we don't need to visit. So we'll coalesce it. We'll throw away everything we don't need to visit, make our tree much smaller. Then we'll run our dual tree k-means algorithm, which I haven't yet described, on the coalesced tree of points and the centroid tree. Once that's done, we'll expand our tree back to how it was before. And then we'll...
Sorry, what is the coalesced tree again?
I will explain it a little bit later. So maybe you can hang on. But basically, I'm going to throw away the parts of the tree that I don't need to visit, which I've determined to be statically pruned. This will make more sense in a couple of seconds, a couple of minutes maybe. Then lastly, we're going to extract the centroids from the tree using the information we've gathered. Yeah?
Sorry, I'm kind of lost. So how do you build a tree out of points and build a tree out of centroids? What does that mean? Can you draw an example on the board?
Yeah, sure. I can draw an example on the board. I am developing this algorithm in a tree-independent way, so I'm not going to restrict how we need to build this tree. But let's say I have a couple of points here. If I'm building, say, a KD tree, what I will do is I'll pick a dimension. So let's pick this dimension. We have 2 dimensions. Then I'm going to find, say, the mean in this dimension, which I think will look something like this, maybe. I'm going to split the points along the mean. Okay? So I get 2 nodes that look like this. And then my root node has these 2 as children. Or actually, this bounding box can be a lot tighter. So, yeah. Well, it's not erasing. That's OK. And then I might, at the next split, I'll split on the other dimension. So I'll split each of these nodes. So for this node, the centroid will be, I hope I'm getting this reasonably right, but we'll split by something like this, and one node will hold only this, and the other child will hold this. And then I can do the same thing here, and I'll get these 2 children. Does this make sense reasonably? Yeah, basically I'm organizing my points hierarchically, somehow.
So KD tree is an example of a space tree?
Yes.
Yeah,
Yeah, there are many other types of trees. You've got the R tree, and the R tree has like 1 billion variants. Vantage point trees and metric trees, random projection trees, these all should fall into the definition of space tree.
So what's an example of a dual tree algorithm then?
Dual tree nearest neighbor search. Actually, this is an example of a dual tree algorithm. So once, the what?
The entire thing?
To get the dual tree algorithm,
Yeah.
I take my tree, I combine it with the dual tree traversal.
Oh, I mean, what's an example of a dual tree traversal?
Let's say we do dual depth first, okay? So I visit a combination of query node and reference node, and if I don't prune it, then say each of these has 2 children, what I'm gonna do is I'm gonna recurse like this. I'm gonna go left, left, so query left, query left, reference right, query right, reference left, and query right, reference right. And so I'll repeat this procedure. So it ends up being depth first search, but it's depth first search in 2 trees simultaneously. So it looks a little more complex. I could also do breadth first search. So I guess I didn't actually talk about the breadth first or the depth first portion there. I recurse into all 4 combination children, and then I recurse down in the first. That makes it depth first. But if I had just gone across all 4 and then made my next level and gone across all those combinations, does that make a reasonable amount of sense? Yeah, okay. There are some complex traversals out there, but again, all we need is that we visit combinations. Yeah?
I have another very basic stupid question.
Sure.
Which is, I hadn't heard of these dual tree algorithms before, so can you just, at a high level, explain how we get savings from having this query and reference tree?
Yeah, so let me run back to this here. So in this particular...
In any application, not just in your application. Oh, okay, this is range, fine. Perfect.
Yeah, this is range search. Yeah, so in range search, basically what I'm doing is I'm building a tree on it, and I'm saying when the nodes are sufficiently far apart, throw away the nodes because they can't possibly be in the range we're looking for. So instead of having to compare every possible pair of points to see what our range search results are, we can actually prune away a lot of our work, often at a high level.
I see, because somehow the tree, like where it's stored in the tree, is also related
To where those points live in space.
Right, okay.
Yeah, yeah. Okay, should I keep on moving forward?
So I have another way to say it. Which
Sure.
Is that, if you query for each individual point individually in the best possible tree, it's logarithmic time. But if you do a dual tree for all the query points at the same time as the reference points, it can be constant time per point.
Yeah, I'll pull out this result later when I get to the theory section. Okay, anyway, we were here. Okay, so the last thing I said was once our dual tree algorithm is done, we will extract the centroids from it, and then we'll fill this vector m with how much each centroid is moved, and then we'll iterate. Okay, so now I got to fill in the pieces here. So first, let's actually develop a contract of what our dual tree algorithm will give us when it's done. So at the end of the running of the dual tree algorithm, we'll get these things. So as input, we pass our query tree, which is built on the points, to our dual tree algorithm, and we pass our reference tree, which is built on the centroids. Okay, and we'll get the following things. First, every query node, every node of points, it may indicate whether or not it has a single distinct owner. Okay, and the notation I'll use sort of is related to the way I implemented it. We can call this owner function, and we can figure out if a node has a valid owner and then what that owner is. Every query node will also hold an upper bound on the distance between any descendant point and its nearest cluster centroid. Okay, so for every descendant point, I'll have some upper bound. We'll also have a lower bound on the distance between any descendant point and any cluster centroid that was pruned. Okay, and these 2 bounds are generalization of the probably easier to understand single point bounds. So for every point which is a descendant of or which does not have any ancestors that are owned, so the ancestors were never pruned at some point, it will have some specific owner, C of P sub Q. I'll also have an upper bound on the distance between that point and its owner, and I'll also have a lower bound on the distance between the point and its second closest cluster. And these are the things that I'll use to statically prune things in the tree. But what I'm going to assume for now is that I'm going to have some dual tree algorithm, and at the end of it, I will get these things. This will allow me to flesh out the other parts of the algorithm. Okay? Yeah?
Why do nodes of the reference tree never show up in this?
Because I'm interested in the results for the query points.
Okay.
Yeah, the reference tree is what's built on the centroids. Right now I'm not looking for information for them. So I'm going to cache results for the query points and the query nodes. Okay, so let's start with how I extract the centroids from the tree. This is a recursive procedure. So given any particular node in the query tree after my dual tree algorithm, if that node is owned, we know it only has one specific owner. So add the contribution of that node, which will be the centroid times the number of descendants to the centroid, and don't recurse. If the node isn't owned and it's not a leaf, then we can recurse to a deeper level. And if the node isn't owned and is a leaf, then we add the contribution of each point because we will have the owner of each point. Okay? And so this is made a lot easier by the assumption I made earlier, which is that every point is held in subsequent levels. This is, yeah.
So, okay, when you say a node is owned, that means that all the points that are contained in that node are
All the descendant points. Yes.
They belong to the same cluster.
Yes.
Okay.
Yeah. So if I know that when I'm building my centroids, then I don't need to recurse any deeper. So maybe I've cached the centroid of that node. Actually, I should have cached the centroid of the node when I built the tree. So I can just add that to my centroid and then multiply that by the number of descendants.
Right, right. Okay. Yeah, that's what was throwing off. So yeah, your nodes need to know the centroid of the descendant points.
Yes, and you can cache this when you build the tree for no real significant extra cost. Okay, so I'm going to assume that we've done that. So now that we have our recursive procedure, the actual procedure of extracting the centroids is pretty straightforward. We fill our matrix of centroids with zeros, and then we fill some counts with zeros. And when we update our centroids, we'll also keep track of the number of points that are owned by each centroid. So then we get our unnormalized centroids by calling this procedure recursively on the root of the tree. And then we normalize each cluster by dividing it by the number of points held in that cluster. Okay, and then we return our centroids, and we have our centroids. Okay, so now updating the tree. Once we've extracted our centroids, maybe we've come back around, we've started the next iteration. And our goal is to prune away work that we can determine that we don't need to do. Okay, so we'll do a handful of things. First, those upper bounds for each node, which represent the maximum distance between any descendant point and its nearest centroid, we need to loosen those by however much the centroids have moved. Because remember, we have this m vector of how much centroids have moved. Okay? And we also need to loosen those for every point. We also need to loosen the lower bounds. We need to decrease them, again, because the centroids could have moved between iterations. Okay? Then we want to determine nodes whose owner can't change during the next iteration. Those nodes, we'll mark them as statically pruned. We won't even consider them. We also want to determine points whose owner can't change, and we'll mark those points as statically pruned. Okay? So now this static pruning process, suppose,
so
yeah.
When you say loosening these bounds, you just loosen them by doing triangle inequality, or?
Yes.
Okay.
Yeah, that'll be what it ends up being. It's there are some if statements in there, but that's basically what it is. Suppose some point p sub q it has some owner c sub I. Okay, so here's my point p sub q, and the owner must lie inside this upper bound ball. That's what I know because this u of p sub q is an upper bound on the distance between p sub q and c sub I, somewhere in here. I also have a lower bound on the second closest cluster distance. So I know that no centroids may lie in here, and the next closest centroid has to lie out here somewhere. Okay, so that's what I learned last iteration. Now I can adjust these. If I increase the upper bound by how much the cluster that owns this has moved, because I have that information, and then I can also decrease the lower bound on the second nearest cluster by the maximum movement of any cluster. Okay, and so in this particular case, the upper bound ball is still contained entirely within the lower bound ball, so we know that only one centroid can exist in here. Thus, we can mark this point statically pruned. Its owner cannot change. And so what the actual computation that we do here is if the upper bound plus its adjustment is less than the lower bound minus its adjustment, we can prune. Okay? We have another strategy for pruning. But before that, here's a quick example of what happens if the lower bound is now too small. Now we can have a centroid that lives in the distance between the two balls here, and we no longer know that only one can own it. Okay, so in that case, we can't prune. We have one more strategy. In this case, take our point and take our centroid. In this case, I've drawn the centroid because it makes drawing this figure a lot easier. And we also have our upper bound. So we know that the centroid must live within this ball, although we know that also that it lives right here. Okay? Now suppose that I knew the distance between the centroid c sub I and its nearest other centroid. Okay? If I knew that, Then once I adjusted this upper bound, so I know that C sub I must lie in this ball, if I draw this ball here, because the distance between the closest centroid, C sub I, and its nearest neighbor is at least this much, there can be no other centroid that lies inside the dotted ball here. And because this completely encapsulates the ball with, of radius adjusted upper bound, then the point's owner can't have possibly changed. Okay, so mathematically, this is if the adjusted upper bound is less than 2 times the distance between the centroid or the owning centroid and its nearest other centroid. Okay, so somewhere during this update tree process, I'm going to figure out every centroid's nearest neighbor. Okay, so that's a black box nearest neighbor algorithm that we can use to do that. Okay, if the distance is not large enough, then we could have a centroid that falls into here, and we don't know that it can be owned, so we can't do that. Okay, so here are 2 strategies for pruning points. These actually happen to generalize to nodes too. So if I have a node that has a valid owner, and then the adjusted upper bound for that node is less than the adjusted lower bound for that node, we can again prune. And then the other rule works basically the same. If the node has a valid owner and the adjusted upper bound is less than 2 times the distance between the owning centroid and its nearest neighbor, or its nearest centroid neighbor, then we can statically prune the point. Yeah?
Should we be thinking about, sorry, this probably gets back at the earlier question.
Yeah.
But should we be thinking about your work as a method for trying to speed up queries, or is it also, or is it trying to come up with the best tree? And if so, like, what should we be thinking about comparing either of these things to?
I am interested in coming up with better trees, but that's not the subject of this talk. So in this talk, I'm basically coming up with an algorithm so that I can accelerate a single iteration of the k-means algorithm. Okay, so I'm showing how we can use dual tree algorithms to do this in a reasonably easy fashion. I have 1 or 2 more pruning rules. The first is if every descendant point of a query node is statically pruned, we can prune it. There's no work to do there. And if all children of a node are statically pruned, we can prune it too. Okay, because the children are pruned, there's no reason to go there. So I'm not actually going to show the update tree function because it's quite complex. So I'm just going to write on the side that what we get out of this is correct, and you'll have to trust me past there. I would say you could reference the paper, but because this is like, I haven't written the paper yet. This is like brand spanking new. Great. So now we have our static pruning rules. What we get is, say our tree, in this case, I've colored the red nodes. We can take those as to be statically pruned. And the blue nodes haven't been statically pruned. Okay? So coalescing our tree, remember, we don't need to visit the statically pruned stuff, so we can just throw those away. And now, because I've assumed that every point here is going to be held in some child, some descendant here, then we can actually coalesce these upwards. There it is. Yeah, so now we get a tree which is much smaller. Yeah?
If you prune a node, does it mean that you could, by definition, you can prune all the points in that node?
Yes.
So are you kind of doing duplicate work by doing points and nodes?
The actual implementation of it, I try to prune the whole node at once. If I can't prune the whole node at once, then I'm going to go through each point and try to prune all the points. But it's possible that the node bounds weren't tight enough to prune the whole node as a whole, but I was still able to prune every point. In which case, I then have to go back and say, okay, now we can prune the node. Yeah. Okay. So we now get our coalesced tree. In practice, this actually tends to be a lot smaller, especially as we get close to convergence of k-means. Okay, so now the last piece that we need to fill in is what are our base case and score functions that actually are our dual tree algorithm. We already established the contract of what the dual tree algorithm will give us. Now let's see how we get that. So our base case gets called with 2 points, the query point and then some reference centroid. And our goal is to find out, does this point own the centroid? Okay, but we'll call this many times, many different points and many different centroids. Okay, so if the point is statically pruned, we can return. We already know it has an owner, and we've already adjusted the upper and lower bounds on it, so we don't need to do any work. If the distance between the point and the centroid is less than our upper bound, then this centroid is it's the new closest centroid candidate. So we take as our lower bound, we take our old upper bound, and as our upper bound, we take the distance between the point and the centroid, and then we update our current estimate of what the owner will be. Okay? If the distance is greater than the upper bound, but less than the lower bound, then we just update the lower bound. Okay? And this is our base case. And it's not too hard to sit here and think, if I called the base case with every point and every centroid, then I would get valid lower bounds, valid upper bounds, and valid owners for every point. Okay? Yeah.
little confused now. So these upper and lower bounds are being separately maintained for nodes and points?
Yes. Each point has an upper and lower bound, and each node also has an upper and lower bound.
And the upper and lower bounds for a node would just be the largest upper bound for a descendant point and the smallest lower bound for a descendant point? Or
Yeah, but they're not constructed like that.
But they will maintain.
That's what they represent, basically.
No. I'm asking, is that going to be a consistency that will actually be present in the numbers or not?
Yes.
Okay.
Yes, the upper bound for a node is a valid upper bound for every point.
But it needs
Is that
to
what
be
you said?
equal to.
Need not be equal to. It could be a little bit
In
looser.
your calculation, you might end up having different.
Yes.
Okay.
Okay. Did I answer that all right? Did you?
This is why you need the two different rules, right?
The two different pruning rules?
Right.
Yeah.
So how would it not be equal to one of the points in this descendant set?
The way that, so here, let me move on from the base case here. Actually, no, I don't want to do that yet. The way that I will find the upper bound will be the maximum distance between two nodes. This could be greater than the maximum distance between any particular descendant combination. So the bound could be loose, but it will still work for pruning. Okay? So if we've all reasonably convinced ourselves that this base case is right, which hopefully we have.
But if you're
yeah.
maintaining the bounds on points, why can you not just define
Quadratic
the...
explosion. You don't want to be quadratic. You just want to operate node by node rather than.
That's right. So the nodes have to abstract the points beneath them.
Yeah.
Yeah.
So you can be looser on the macro level because you don't want to suffer the quadratic overhead.
Yeah, I'm not updating the point bounds until I get to somewhere in the tree where I'm actually holding points. Okay, so if my tree only has points at the lowest level, then I won't actually call this till I get to the bottom. And hopefully I pruned away most of my work by then based on the node bounds. Okay, so the last piece is the score function, which is fairly complex, so I apologize for that. As input, we have a node on the query points, and we have a node on the reference centroids. Okay, so the first thing we're going to do, if the node is pruned, we return infinity. It's pruned. We don't need to do any work. We're done. Okay? Next, if we haven't yet visited this node, then the parent could have a valid lower bound. The parent may have pruned something, and the lower bound is only a lower bound on nodes that have been pruned. So we need to take that parent's lower bound if we haven't yet visited this query node at any time during this traversal. Okay? Then, let's ignore the first line here. Let's take this piece by piece, but I have to put this here for scoping reasons. If the minimum distance between the query node and the reference node, so that's the minimum possible distance between any descendant point and any descendant centroid, if that's greater than the upper bound, then I already know that there must exist a better centroid for every descendant query point. Therefore, I can mark the reference node as pruned. Okay? And because it's pruned, if that minimum distance is now less than the lower bound, which is the lower bound on pruned nodes, I can update the lower bound. Okay? Now, suppose that this isn't true. Suppose that I can't prune the node. Okay? I'm going to pick a centroid out of the reference node. Just however I do this, doesn't matter. I'm going to pick one. And then I'm going to take the maximum distance between the centroid that I've picked and the query node. So this is a maximum possible distance between any descendant point in the query node and in the centroid that I picked. If that's less than the upper bound, then I know that the C sub D, the centroid I've picked, is going to be closer to all of the descendant points. So I can update the upper bound, and I can take this as the tentative owner. Okay? Now the last bit, if I have been counting what I've pruned, and I notice that all the clusters except one are pruned, then we can say, oh, that owner here, which I haven't necessarily marked this as a valid owner, I'm just holding C sub D here, that owner now must be the valid owner of all of the descendant points of the query node. Okay? So I can say, I can mark n sub q as a valid owner, and then I can return infinity, because I don't need to go any deeper. Okay? And then the last little bit, we need to return infinity if we marked our node as pruned up here, and otherwise we'll return a score for recursion priority. Okay? And you can do a correctness proof on this. I don't really have time here, but basically the way it works is we show that base case is correct if we don't prune anything, and then we show that we don't prune anything that we shouldn't have pruned, is the basic strategy here. Okay, so that said, if there are no questions, let's move on to the results. I'll start with the theoretical results. So remember that this algorithm I've come up with is independent of the type of tree used. So I can say, well, let's use the cover tree, and then let's use the traversal that goes with the cover tree, okay? And when I've said this, this actually brings in some interesting theory. So the cover tree depends on the expansion constant, which is sort of a measure of intrinsic dimensionality, okay? So this is the measure I was talking about when there was an asterisk in my earlier bound, okay? So I assume that my data set is well behaved, and I therefore assume that C doesn't scale with N, okay? So I'm going to make that assumption for these theoretical results. And what do I get? Each node has up to C to the 4th children. Oh, yeah, I didn't say, yeah, okay, yeah. So the actual definition here is given some data set, the expansion constant is the smallest C greater than or equal to 2, such that for every point in the data set, I'm going to take a ball centered at any point of whatever radius, and then I'm going to double the size of that ball. The number of points contained in a ball of twice the radius can be no more than C times the number of points in the original ball. That's somewhat related to the doubling dimension. Okay, so when we assume that this is well behaved,
For all delta?
yes, for all delta too. I'm sorry, I've dropped the ball here. Yes, so for every point in the data set and every possible radius that's greater than 0. Okay, so assuming that, we get that each node in a cover tree has depth of O of C squared log n. We also get bounded tree size, which is nice. Every cover tree has no more than O of n nodes. And then we get a bounded construction time of C to the 6 n log n. And this isn't my work, this is John and friends from some years back. But I will now pull in some of my own recent work. Some co-authors and I recently showed that if I have a general dual tree algorithm, so just a dual tree algorithm where I use the cover tree and the traversal and then whatever base case and score, then I get O of n time for a query set of size O of n, plus lots of little factors. I'm not going to go into the little factors. So my proof strategy to come up with my result will be first fill in the easy little factors. Okay, that goes pretty straightforward. Then I'm going to say our base case and score look really similar to dual tree nearest neighbor search. We're going to be able to show that our pruning is at least as tight as that. Okay? Then we can use the results from dual tree nearest neighbor search, which are the expansion constant of the reference set to the 9th times n plus theta, where theta is a measure of how good our tree is, which generally will scale sublinearly or linearly with the tree size, or with the size of the data set. Okay? So we can just use that result, and what we end up with is that our dual tree traversal, not the whole algorithm, but just the dual tree traversal part of it, it takes the expansion constant of the centroids to the 9th times n plus the imbalance of the tree. Okay? And if I've already assumed that the expansion constant of my data is well behaved, it's not really a stretch to say that the expansion constant of my centroids are well behaved because they also arise in some way from the data set.
So how should I think of theta? Is the constant like sublinear in n?
Yes, sublinear or linear in n. This is, I don't have, the tightest bound I can show right now, so this is a real recent work, and I'm hoping to tighten this, but the tightest bound I can show is n times the aspect ratio. But empirically what I see, when the tree is well behaved, then I get sublinear or linear scaling in the size of the data set.
So you said times.
I was just going to ask, what do you mean by the tree being well behaved?
What I mean is that the cover tree is it's a leveled tree. So when I build the cover tree, I have a number of levels. Okay, and so this is like, say, level 0, this is level 1, and then this is level 2. Okay, so what the imbalance actually is it's a count of the number of missing levels. So here I've drawn a missing level. This node has a child that's 2 levels lower. Okay, so my imbalance is actually just a count of missing levels. And
by aspect, so aspect ratio can be
the furthest pairwise distance in the data set divided by the nearest pairwise distance. Okay, this is the tightest bound that I have, but I think you can prove tighter. I haven't gotten there yet. Okay, so what I'm going to say for now, with not all that much support other than empirical support, is that theta is reasonably well behaved. Okay, I want something better than this for the paper. I'll get there. Now we can do our runtime analysis. And remember our update tree step? We assumed that we had the nearest neighbors of every centroid. We can just plug in the nearest neighbor runtime result here. So we add up the time for all of our pieces, and we get that the whole iteration takes k log k plus the expansion constant of the centroids times n plus theta. That's how long a single iteration takes. So now the asterisks are mostly removed, and this is about the scaling that we get per iteration, worst case. For memory analysis, our cover tree takes O of n space, and storing the centroids takes O of k space. And we won't use more than O of n memory during the traversal. So we get O of n plus k memory usage for cover trees. For other types of trees like KD trees, we'll see n log n plus k usage. Okay, now let's get on to the actual experiments. Yeah.
So is it, I guess you're really expecting these C constants to be completely independent of K and dimension, all of these problems.
That is the assumption for the cover tree bounds, yeah.
And is that a practically valid assumption?
Reasonably, yes.
Okay, because
So
you have some rather large exponents.
Yeah. So in practice, these bounds, so let's go back to this here. If I actually calculated this number, if I calculated the expansion constant of the centroids, this number would probably be huge. The assumption is that C doesn't scale with n, so that as I make n larger, then the scaling characteristics. So like I can't use this bound as just calculating.
But also with K, so if you're talking about the centroids, then probably you also want it to be independent of K, right? Because you want to scale to large K, that's your motivation.
Right, and so all of the other algorithms have scaling that's O of k times n. This is O of k log k plus n. So in that sense, we've improved. As long as we're making the assumption that the data is well behaved, which for a reasonable number of real world data sets, it is. Okay? So moving on from the assumptions, let's get down to the actual results. So I've implemented everything here in mlpack. We can run it pretty easily just from the command line. We specify the data set, the number of clusters, the initial centroids. We want to start from the same place, and then the algorithm we want. So dual tree, blacklist, Elkin, Hammerly, and naive. In some cases, I've actually done a better job of implementation than the reference implementation. So the blacklist algorithm actually prunes tighter than what I would download off the author's website. I picked a handful of data sets, scaling from 40,000 points to 6 million, and a handful of dimensions. They come from a variety of settings. For initializing my clusters, I'm going to use the refined start algorithm, but when n and k gets very large, this takes an extremely long time, so in those cases, I've just used random initialization. Okay, so what I'm going to show now is a lot of numbers, and what the numbers are the average number of distance calculations per iteration of the algorithm. So I run the algorithm, I count all the times that I called my distance oracle or whatever, and I divide it by the number of iterations, and I get lots of numbers. Okay, so what I can see, and I've organized these data sets so that the small ones are at the top, and we get down to the large 6 million one at the bottom. What I can see is that for small data sets, the overhead of trees doesn't pay off. Elkin and Hammerly's algorithm just dominate. But as the data sets start getting larger, and as k starts getting larger, the dual tree algorithm does less and less work, and then eventually, if we get large enough, Elkin's algorithm runs out of memory because it uses k squared plus kn memory, and blacklist algorithm actually runs out of memory too for my largest implementation. Now, you could call this a cop-out. If I did buy a computer with more memory, yeah, I could get it to run, but the scaling that I'm seeing, I would expect it to be way slower anyway. So these aren't, yeah.
So when I was playing with the cover trees a long time ago, one thing that I noticed was that it's not just the amount of distance computations, because all of the if then else stuff.
Yeah, and so
slow things down.
I have runtime numbers next. Okay, also I forgot to say, for these simulations, I've used the KD tree, not the cover tree, because I have a bug in my cover tree construction code that I haven't worked out yet. But I will get numbers for that at some point. And I expect them to be reasonably similar. They should exhibit the same characteristics. So runtime, as you were saying, is a more interesting measure. And I do see that, yes, because trees are jumping around in memory, whereas Elkin and Hammerly's algorithms are going sequentially. They have cache benefits there. We don't get that. So the tree algorithms are somewhat slower. But at some point, again, the overhead no longer matters, and we get an algorithm that works better in our desired region of interest. And the dashes here, I just actually haven't bothered to run the naive algorithm because I don't want to wait that long. Okay, so that said, let's make some conclusions about dual tree k-means. First, we get exact results. This is not an approximate algorithm. We're doing exact same thing. In the worst case, if we make some assumptions about our data, then we get O of n plus k log k about time when we use cover trees. It takes no more than O of n plus k memory when we use cover trees. And importantly, we can use it with any type of tree and traversal, right? It's modular. All we have is a base case and score function. We specify our type of tree, okay? It will work best. Our pruning rules are tightest for traversals that are breadth first in the centroids, okay? That's how these rules happen to work. Lastly, it's empirically the best algorithm for large enough n and large enough k, okay? So now a couple of words quickly on where we can go from here. First, kernelization. People say, well, k-means isn't interesting. I don't want to do kernel k-means. Well, but we can. Some trees, including the cover tree and metric trees, they just need a metric. Okay, well, here's a metric. Given some kernel, that I can evaluate. Here's a metric, here's the distance between 2 points in kernel space. So I can just plug this in, and now I have a tree that's built implicitly in kernel space. This is great. Now I can adapt my algorithm reasonably and do kernel k-means. Okay? At first glance, which is all that this idea has had so far, now every distance calculation between a point and a centroid takes O of n time, because I don't know exactly where that centroid is in kernel space, and I can only represent it as a sum of the the kernels between the query point and all of the points that are owned by that centroid. Okay, so what we end up with then is scaling that's more like n squared plus kn log kn. But we can compare this with O of kn squared, which is the naive case. Okay. In addition, kernel k-means, we can see this and we can easily generalize to other spectral clustering techniques. So there are neat directions to go there. Okay. Now the next question, which I said I'd put off for later, if we're doing, why are we doing exact nearest neighbor? Maybe we want to do approximation. Well, approximation with trees is actually easy. Remember that our bounding rule looked kind of like this. Take the minimum distance if it's greater than the upper bound prune. We can adjust this. Take the minimum distance if it's greater than the upper bound minus epsilon. For some epsilon, then we can prune. This is absolute value approximation. We can also use some other notions of approximation. Okay? We can also apply this idea during the static pruning process, and we can save some work. We can make it even faster. Okay? And the next idea, and probably the most interesting idea, in my opinion, is parallelism. So it's really kind of unfortunate that this is all I have to write on the slide about it. That's why I've included a picture of a shark with a laser on its head. So parallelism, remember we have trees, we have traversals, and we have our base case and pruning rule. Okay? Our tree and our base case and pruning rule can be completely independent of the traversal. And the traversal can be the part where we have the parallelism. So I can have my massively distributed parallel, or I can have my traversal that runs on GPUs, and the guy who wrote the tree and the guy who wrote the algorithm doesn't have to worry about it, right? So this is actually what I will be going home to do this summer. So wait on more results. Sharks with lasers will be coming. Okay, so let's take a kind of a look at the landscape of what we have as far as dual tree algorithms. We've got trees, traversals, and problems we can solve. So here's kind of a subset. We got a bunch of types of trees, we got a handful of traversals, and we have some problems we can solve. Okay, so I've shown new tighter bounds for nearest neighbor search. I've shown with the co-author that we can solve the problem of max kernel search with the dual tree algorithm. I have a faster KD tree traversal. I just showed you k-means. That can be generalized to spectral clustering. And I just talked about a parallel and distributed traversal. I also have a better idea for a high-dimensional tree, which will allow us to do approximate kernel PCA. And you can even train HMMs with a dual tree algorithm approximately. Okay, so now we have all of this stuff. How do we choose how to put it together, right? So if I pick my problem, then the best tree and the best traversal for that particular data set, picking this might actually be hard. So we could just, pull the lever and use the cherry tree, but this may not actually be the best thing to do. So maybe a better solution is a black box. Okay, our user can pass in their data set, the problem that they want to solve, and maybe whatever parameters go with that data set. And then inside the black box, we can take a look at the properties of the data set, and we can make a smart decision about which tree we're going to use, which traversal we're going to use, and maybe even which set of pruning rules we're going to use, okay? And maybe the user can override these with their preferences and we get results, okay? This is important because people at the higher level from what I'm doing can just use this stuff. They don't need to know about trees, okay? And we can even go a step further than that and say our black box doesn't just need to be around dual tree algorithms. It can actually just be around k-means. Right? It's a black box for k-means. Decide which of these 5 algorithms we're going to use, and if we're going to use trees, then recursively call the black box for trees. Okay? So some conclusions of the talk here. First, dual tree algorithms are fast. And in some cases, we get compelling theoretical guarantees. Second, we can solve a surprisingly large number of problems with dual tree algorithms. Third, there's no good k-means algorithm for large n and large k, or there was no good k-means algorithm because we can develop a dual tree algorithm for that case, which has asterisk runtime bounds and O of n plus k memory usage, right? It performs pretty compellingly when we use it in its designed operating region, and if not, make your data sets larger. You can use it. You can go download mlpack off GitHub and just use it out of the box as easy as I showed. And improvements in parallelism are coming, and it won't just be to k-means. It'll be to dual tree algorithms as a class. Okay, so this concludes my talk. Any questions? I hope I didn't talk too long.
So there's a different kind of tree that I guess we've worried about here, which is suppose you want to just do multi-class classification and you want to do it very quickly.
Okay.
Then you have a large number of different labels, potential labels.
Yeah.
And now the way that you want to actually make splits at the nodes is much less clear because it's some sort of learning problem at the nodes, right?
Right.
So this is a rather different kind of tree from what you talked about. But I'm wondering if you've thought about this and whether or not it could transfer. Any of these things could transfer.
A little bit. Suppose that I have, actually, let's use k-means as a classifier, right? So basically, the label that I choose is the label of the nearest centroid, or just the nearest centroid, nearest cluster, whatever that is, okay? In this case, my decision surface actually makes sense in some space. And I can build a tree, as I did here on the centroids. So I can quickly throw away stuff that's very far away, okay? So maybe I can think about this more for generalized models in some other space. Does this, I'm postulating. This isn't an exact answer.
Something where you run your k-means algorithm, and that gives you some splits, effectively, and then you use that to define the tree and what you're going to learn which split to use.
That wasn't exactly what I meant, but I don't see why you couldn't do that to kind of come up with a tree where basically you say, so I have some very high level classifier or something like this. And if it classifies left, then I get a bunch of lower grain classifiers on the left. And if it classifies right, I get a bunch of lower grain classifiers on the right. And you do this hierarchically and iteratively. I don't see why it couldn't be done, but I don't have an exact solution for you here now. Whoops. Yeah.
Do you have thoughts about using your machinery to choose K, to choose the best K?
No, I haven't thought about that. I know that the guys who did the blacklist algorithm did then do some further thought on an algorithm called X-means, which is, I believe it chooses K based on the BIC after it runs every iteration. I have not thought about going that direction. My interest here was, can I do K-means faster? And it turns out I can.
So maybe related to the base question, have you think about like some kind of agglomeratic clustering like approaches? So rather than just purely just solving for K, can you maybe just show some kind of like that?
Yeah.
So the tree should lend itself naturally to returning some kind of a hierarchy.
So I thought about agglomerative clustering for a while. Single linkage clustering actually in a Euclidean space, say, turns out to be the minimum spanning tree. You can actually do that fast with trees, so somebody already planted their flag, I can't do that. I sat next to him though, that counts. So you can do that. I think it is possible to extend to other types of linkages, like complete linkage, but I think you can only do that approximately. B matching is another example of a similar type of approach you could possibly use hierarchically. But again, that I think you can do with trees. I think you can only do it approximately. Yeah.
Can you say more of why you would want to use K in the thousands? It sounds like a recipe for overfitting.
It depends on what you're doing. Say I'm training a code book for vector quantization. This is the most compelling example I can find. People actually do this. The vector quantization algorithm, as it was originally given like 40 years ago, is something that's very similar to k-means. So people still use that and k-means as just black box, I want 4,000 clusters. We'll hope there'll be a decent representation. Is that reasonable? Yeah.
I've heard of examples where people are trying to do 100,000.
For that type of thing or something?
No, not for that kind of things. For like search.
Do you feel like it's like a well-motivated example though? I mean, if people can do it, but I mean like the vector quantity seems to be.
Yeah.
Certainly, in the situations where you need to have a large amount of representational power, and you have a large amount of data. So, to some extent, at least, well motivated. Whether that would actually be helpful, I think is less clear.
Yeah, the biggest applications I could find were in the thousands or tens of thousands. But you say people are doing hundreds of thousands? Maybe I'll start saying that. Okay, well, thanks for listening.